Hello guys, welcome to the third part of Microservice series. In part first, we have discussed that why we should use microservices, what are advantages and disadvantages of using microservices, and also we have discussed about decomposition pattern which is used to create or decide microservices. In decomposition pattern, I have discussed about decomposition by business capability, decomposition by subdomain, and strangler pattern. In part 2 of the series, I have discussed about integration pattern. In integration pattern, I have discussed API gateway, aggregation pattern, and composite UI pattern. In this, in the third part, or in current video, I am going to discuss about the database pattern. Under the database pattern, I am going to use or I am going to discuss database per service, shared database per service, API composer, CQRS pattern, Saga pattern, and event sourcing. Database is always a important part of any application. And in monolith application, we have a separate structure of database. But with the microservice architecture, we need to change in the database design as well. So I am going to discuss that what are the best practices, what are the design principles we should use while designing microservices in respect to database. So the first pattern is database per service. Ideally scenario that every service has its own database and accessible only via its API. So why it is required? Many people ask that what is the need of using a separate database per service? Why can't we use a common database like in monolith application and we use can't why can't we use separate services? So, what is the purpose of using microservices? We are using microservices because we need a system which is loose coupled, a system which is independent of other changes, and a autonomous system. So think you have one database and that is being accessed by all the services. And that database there is one table like customer and you are going to change the schema of that table. It might be possible that table is being used by other services as well. So, can you change the schema freely? No, because that schema or the table is being used by other services. You need to coordinate with other services if they are using that is table or not. And if they are using the table, if there is an impact of a schema change, if there is an impact of a schema change, then they need to change at their side as well. So you have a dependency on other services. You can't do the change standalone or independently. So that's why we need a separate database. So how you can keep the separate database? There are three type or three way you can do database per service. You can use private table per service. So you can keep one table for per service. The second approach is use a logical schema or logical DB schema per service. And third one is having physical database server per service. So if you are going to use private table per service, it might be possible that your table is being used by other service developer because there is no restriction. They can be used. If we are going to use database physical database server per service, then also it's very costly and it's very tough to manage because you need to see the other aspect as well. So the best part or best thing is use logical DB schema per service. Create a logical DB in a physical server. So in logical DB, the separate file is being written. You can do your work independent of others. You can change your schema or you can do anything like that. The advantage of using database per service is it make your system loose coupled. So there is no tight coupling now. Your system is now loose coupled. You can do your own change without fearing that if your change is having impact on other service or not. Second, change in a schema of one database table does not impact other service because the table is being used by your service only. So if you are doing your change schema of the table, you are sure that this table is used by me only. So I need to see in my service if there is impact, and that will be minimal. And also, you can choose your own database type. So depending on the requirement, you can use either RDBMS or NoSQL. So there is no restriction. There is also some disadvantage of using this approach as well. So first, business transaction is not easy in this decision or in this design because in practical scenario, the transaction is span in multiple business capability. So if you have a user and customer, so when you have a order and customer, so when an order come, you might need to check if that customer has valid credit point or not. So you need transaction. But now you have two tables, two database and two service. So transaction management is not simple. For that, we have Saga pattern that I am going to discuss in further slides. Second disadvantage is if you are going to query or if you need a data that required from multiple tables or multiple database, it's not simple because now every database is owned by a separate service. So ultimately, you need data from three services. So for that, we have other design principle that I will discuss later. So this is simple architecture. So you have a order service. Order service will access order DB and customer service will access customer DB. Order service can't access customer DB directly. So if order service need the data from customer service, he a order service need to call the customer service. Customer service will call the customer DB and give that data to order service. So there is a restriction. You can't use directly order service to customer DB. Now, second design pattern is shared database per service. So it allow different different service to access data from same database. Like order service and customer service can access the same database which have order table and customer table. So when this kind of scenario come, so as I discussed, like in strangler pattern, we are going to migrate our existing monolith application into microservice architecture. Now, in that application, you have already database which has joins, restrictions, which is already normalized and that was designed based on some monolithic application. Now, it's very tough to decompose that database. So, in that scenario, you can keep the same database. The advantage of using shared database per service is it is easy to implement ACID transaction to ensure data consistency. Because all the services are using same database, you can easily implement the ACID transaction. It is very simple to operate because then you need to maintain only one database. The disadvantage of using shared database is that if there is any schema change in one table, developer need to coordinate with other service owner if there is any impact. and it defeats the purpose of microservice architecture. So that I already explained that why we need separate database per service. And also wrong code in one service can block other service. So if your service A is writing some or updating some records in table, and at the same time if service B also going to write or update the record in table in the same table, it might be occur or log condition can be occur or deadlock can be occur. Now it is very difficult to identify or debug that way the problem. In monolith application, because you have only one application, so you can easily find, yeah, you can easily debug from any tool. But here you have multiple services and each service is deployed in different VS. So it's very tough to find that way the problem. The third pattern is API Composer. So, as I discussed in database per service pattern, that the disadvantage of using that service is querying. If you want to query the data from multiple database, how to do that? So for that, we have API Composer pattern. So API Composer is used when you need to get the data from multiple services. It invokes services which own data and perform the in-memory join of result. So if you need data from order service, kitchen service, or delivery service that give you data from order DB, kitchen DB, and delivery DB. So what API Composer will do, it will call or it will get the data from this service and then join the result and give the response to the customer. Now, fourth pattern is CQRS. This is command, query, responsibility, segregation. So what is command and what is query? So command is like create order. Create order is command. Do delivery. This is command. So command result in an event. So when give a command to service, create order, this event because of that command, that is order created. So order created means it changed the state of order. It changed the state of order. So a command will change the status and generate an event. A query, it will return the data from DB but don't change the status. So like if you want to know the status of order, you will query from database and check what is status. Command, you will it will change the it will change the it will create the event and change the status. So I am saying order create order is command. Because of that, order created event will be generated. It change the status of order as created. Then the second command do payment for this order. So payment done and then so the status of order is now payment done. Third is stock check. So the status is stock checking. So that's why by different commands your state of your entity is going to change. So there is one pattern that I will discuss later, that is event source. So in event sourcing, what we are doing, we are storing all the events that are generated because of commands. So if at any time, like you have a commands, create order, do payment, do stock check, do delivery. So at any time, if you want to know the status of order, it is very tough to find in event source because it is having multiple records. Also, as we discussed in earlier, that we are using API Composer to get the data from multiple database. So here you see that we use the same database order DB to write the data and read the data. So it is not it is not a good idea, because if any time any write is happening and you are going to read from the database, your read will be stuck, because write will block the records in the database. And usually what happen, that in any application we write 10% and read 90%. So the better approach is to let separate database for these two type of operation. Let have different database for read and different database for write. It is useful when you need to retrieve data from multiple database service and when you applied event sourcing pattern. So let have an example that how you can use CQRS to retrieve data from multiple database. So so I'm going with e-commerce website. I'm having order service, I'm having kitchen service, and I'm having delivery service. And this service has their own database. So now one command come create order. It create an event that's order. It generate the order in the database, and then what it will do, it will publish that event into the queue. Same way in kitchen service, one command come like do this or prepare this. So kitchen service will generate the event depending on the command and send that command or send that event to this queue. Same way, delivery service, it got a command like do the delivery of this order. So it will store in delivery DB, and also whatever event generated because of this command, it will send that event to delivery event. Now we have a separate service which is order history service. So order history service, it has a handler, event handler, which will listen from order event, ticket event, and delivery event. And it will store all those events in the view form. So I don't think they need to discuss what is view. So it will denormalize the data and store in this table so that your retrieval will be fast. So now if any query come to which need to get the data from order, kitchen and delivery, it is going to call this service order history service, and this service will get the data from database. Since database are denormalized in this table, it is very fast and it give you data. So now this database and this database are different. Order DB, kitchen DB, and delivery DB is used only for write operation, and this view database is used for read operation. So if any write is happening at the same time, if any read operation will come or read query will come, it will not impact it because we have separate database. So the benefit of using, so let me cover and how we can use CQRS with event sourcing. So as I told that event sourcing is to store every event, to insert every event in the event store. So we are not going to update any event, we are just inserting all the events. Now, if you want to know that what is the status of my entity at any time, how you come to know? Like you have event, order created, payment done, stock cleared, delivery done. So now you customer want to know that what is the status of my order. So if you are going to query from this database, it is very slow because you need to query from 4 5 rows for that order. Now that there might be many orders in that table. So what we do that we store the final status in the read database as well. So we got a command like create order. This command service will store that event into event store and also publish that event into the MQ. We have an event listener that will listen from that MQ and it will store into the read database. So whenever any query come to check the status of order, what it will do, it will hit this query service and query service will get the data from this read database easily. So that's how this CQRS and event sourcing is working. Now, what is the benefit of using CQRS? So first benefit is it improve performance as read operation is not getting blocked by write operation. We have two separate database. So anytime if you want to read, you will use the separate database and that is also denormalized. You don't need to join multiple tables. So your read operation is fast and your, and also in write table you are going to only write the data. So your performance is improved. Second, in event sourcing pattern, you can get the status of any entity anytime easily. The drawback of this CQRS is it increase the complexity because now you need to have this mechanism to publish that event into any queue. Then we have other service that will listen from this queue, store from in this separate database. So it increases the complexity because this is only three services, but you might be have many services in real world. Also, one thing to be note that this CQRS is having eventual consistency with high availability. So, so there is cap theorem. In cap theorem, we have three parameter. One is consistency, second availability, and third is partition tolerance. And theory says that you can achieve only two out of these three. Either you have a consistency and availability or consistency and partial tolerance. So you can have three out of, or you can get only two out of these three. In consistency, we have two type of consistency, either strong consistency and eventual consistency. So what is strong consistency? That all the node in the distributed environment having the same copy. There is no time lag as well. So if you read from the database, every time you get the same record. Eventual consistencies that your write database and read database, or if it is distributed network of database, then your two node of database may have different data, or there is some time lag. So, for example, in this system, you can see that we have an order service and order service put the data in order DB and then it publish that to order event and then order ST service will insert that data into this view database. Now, there is some time lag between these two systems because this processing is happening over there. So it it has the eventual consistency. Let's suppose you got a order and it is just inserted into order DB, but it is not there in view database. And at the same time, any customer come and he want to know the status of order, he might not be get the actual data of that order, and this is called eventual consistency. So in CQRS, you can see using MQ pattern, this is eventual consistency. If you are going with strong consistency, then you need to write into database in the same transaction. So you put order DB here, and at the same time you put the record into this one. But then your application is not maybe sometime customer can get the error message because it will take the time and your database is not available because some locking is there. So use this for the operations that are okay with the eventual consistency. Now come to the saga pattern. So we discuss in database per pattern or database per service pattern that every service is having their own database. So now if if a in a business transaction you need to access multiple database, how you can do that? Because every database is being used by their own service. So for that, in microservices we use saga pattern. So a saga, it is sequence of local transaction where each transaction update data within a single service. So you have a steps like order, and you got a order, and then you want to check if that customer is having valid credit point or not. So in that case, there are steps like create order. Second step, check in customer service, check the credit rating or credit point. Third step, customer has a credit point, then order is successful. Fourth step or 3B step, customer don't have valid or enough credit point, then your order will be failed. So these are the steps. So these steps will be implemented in different service. So like in our example, create order will be implemented by order service. Credit rating will be implemented in customer service. So so these steps are the sequence of steps is saga, and so now the question come, who will coordinate these steps of sequence? Who coordinate that after this step, next step will be called, and after second step, third step will be called. So there are two type of implementation. One, event or choreography. Second, orchestration. So in choreography pattern or choreography implementation, there is no central there is no central coordinator to coordinate all those steps. So each microservice will call each other for that. In orchestration, we have an orchestrator that take responsibility of Saga decision and sequencing business logic. So orchestration is called command-driven approach and choreography is called as event-driven approach. So let's discuss choreography. So in choreography, there is no central coordinator. Each microservice will talk to each other. First trigger come from external request, then other microservices started working when it got the trigger from previous servers. So for example, let's take this eBay, or sorry, not eBay, e-commerce application. We have order service, we have payment service, we have stock service, and delivery service. So this command come create order. This command will go to order service. Order service will generate the order in state pending. Remember, the state will be pending initially. Okay. Now it push that message to the queue with the order event, and this order event will be received by payment service directly. So there is no coordinator. These services are talking to each other directly. Now, there are two scenarios. Payment service maybe fail because no money in account, so or payment failed, and payment service can be successful. Payment service detect the money amount from your wallet. If it fails, it will send that event to the queue, payment fail queue, and this will be listened by order service. And order service mark that order as failed and also may mention the reason that because of payment it failed. If payment is done successfully into payment service, it will trigger event payment event and it will be listened by stock service. Now stock service will check if there is proper stock of that item or not. There are two cases. One, stock is there, then it will generate a event, delivery event, and that send that message to this queue. Or this stock service may be failed because that item is out of stock. Then it will send that message to stock out of exception fail queue. Now, this stock out of exception queue, this queue will be listened by payment service and order service. So what payment service will do? It will refund the amount that was deducted in step 2. What order service will do? It will mark that order as failed and mark the region as out of stock exception. So now you can see that these two services are listening to this queue directly. There is no coordinator and also there is no rollback as well. So we are not doing any rollback in each service. We are doing compensation. So we took the payment and then once it fail, we give the refund. Here we create a row in order service, order in pending state, and then we mark that order as failed. So there are multiple records in our database. We are not going to update the same record, and this is called compensation. And delivery service will listen to this event, delivery event, and do the delivery. And once delivery is completed, it send the message to completion event queue that will be listen or that will be connected to order service and order service mark that order as completed. So this is the total life cycle of that full order. You can see that if any fail happen, it will payment service send message to this queue. If success happen, it will send this message to queue. And there is no coordinator. This payment service is deciding that in which queue that message need to send depending on the condition. And then also payment service is listening to out of stock this queue and order service also listening to this queue. So this order service is decided that which queue they need to listen. So there is no center coordinator in this choreography. This is useful. So choreography is good. This is useful if you have few services like 5, 6, 7. But if you have more services, then it becomes too complex. Because now let's see you have 8 services and request fail at 7 service. Then that whatever message is published to queue that will be listened by 7 services or other 6 services. So system become complex if this um, the number of microservices will increase in choreography pattern. So we have second approach that is called orchestration and in orchestration we have a orchestrator that take responsibility of Saga decision and sequencing business logic. So we took the same example of choreography. We have a order service, we have payment service, we have stock service, and we have delivery service. So when create order saga come, the order service will create a saga orchestrator, order saga orchestrator. Okay, and this orchestrator, what it will do, it will send the message to message queue, that is execute payment, or this is payment channel. And this payment channel will be listened by payment service. It will do its processing. It will direct the money for that order, and it will send the reply to the order saga reply channel that yeah, payment is done. Now you can deliver the order. It will be listened by orchestrator. Orchestrator check the status. It is successful. Yeah, it is successful. Then send it to the order channel. This will be listened by stock service. Oh, this will be listened by the stock service. So stock service check if for that item is stock in the stock that item is there or not. So if item is there, it will send the message to order saga reply channel, and that will be received by order saga orchestrator. Orchestrator check, yeah, item is there in the stock. So it will send a message to delivery channel so that delivery service can deliver the item. And once delivery service will deliver the item, it will send the message to reply or order saga reply channel that delivery is done, and it again send to orchestrator. Orchestrator then make the status of order as completed. So this is the flow of orchestrator pattern when everything is successful, everything is okay, yeah, happy scenario. But how this failure is handled in orchestration pattern? So suppose failure happened in stock service. In stock service, it found that this item is out of stock. What happened? So stock service will send a message to order saga reply channel, and message is out of stock reply. That will be received by order saga orchestrator. It will check that a message coming is out of stock. So what it will do? It will send the message to payment channel, but now it is refund client. So it will ask for refund, and then it will receive by payment service. It check, yeah, the message that is coming is for refund. It will do the refund. So that's how it works. So here you can see that order saga orchestrator is a center coordinator, is coordinate what to do. This is good approach, but the drawback of this is that this orchestrator become bottleneck sometime, because this is a center application. Developer used to write logic here more, and then it need to be scale more. So that's the thing. And then last, event sourcing. So I already discussed event sourcing that uh, so what happened earlier, that we used to store the final state of any entity like order. So if it is created, we say status created. When delivery is done, we say delivery done. When payment detected, we said this for order payment detected. So we keep the final status of any entity. That was the early approach. But in event sourcing, what we will do, we store every event that change the state of entity. So if a order come, create order is separate entity, we insert that one. Then payment is separate entity, we keep that entity, we keep that event as well. Then stock checking is separate event, we keep that event, and fourth is delivery, that we keep that event. So we are keeping all the events in event source. The benefit is that you can keep the in audit log. It is beneficial. You can keep that, yeah, what's going with my order. It's you keep a history that, yeah, what's going on, and and it is easy to migrate. So you can easily migrate from monolith to microservice architecture. But problem with event sourcing is that when you are querying from the event sourcing database that what is the status of my entity, it may take time, and that's why we have CQRS pattern that I already explained. So this is the CQRS pattern, that how we will read the state of final state of entity. So we keep the final status here in the read table, and when any query come from the customer that what is the status of my entity, it will just read from this read database and then give it to the client. So that's all about database pattern that we have used. So just recap that we have discussed database per service, we have discussed shared database per service, we have discussed API composer, CQRS, command query responsibility segregation, we discussed Saga pattern. In Saga pattern, we discussed choreography and orchestration, and then we have discussed the event source. So thanks for listening. In next part, I am going to cover other patterns, that is log aggregation, that how to aggregate the log, observability pattern, and yeah, observability pattern basically. Thank you very much.